In this video, I will go over the homework that follows lecture 19.2 that covers the applications of first-order linear differential equations. And as always, I hope that you watched this lecture in which I covered at least two different applications of first-order linear differential equations. And let's go ahead, jump into the homework. And here's the first question. And the idea is very simple. We have a flying object of certain mass, and when the object is moving, its net force produces acceleration a, which is the derivative of its velocity function, but on the other hand, the net force is equal to the sum of all other forces acting on the object. So if we set the coordinate system with the origin at the surface level of Earth and pointing upward perpendicular to the surface, then the following two other forces are acting on this object. It's the weight of the object, which is mg, and however, it's worth mentioning that the weight is pointing downwards, so it has negative sign in the front. And the other force, it's the air resistance force, Fa, but air resistance is always opposite, pointing in the opposite direction of V, so we're going to have a negative sign over here. And according to this word problem, it's equal to negative 0.7 V. So with that being said, we have the following differential equation. And we're going to plug all the values in, and we're going to add 0.7 V to both sides. So here's what we get. We get 0.67 V prime plus 0.7 V being equal to negative 0.67 times 9.8. And we can compute that. Negative 0.67 times 9.8 is negative 6.5. Actually, it's too early for that. You know what? Why am I saying that? Because we're going to divide everything by 0.67 to write it in standard form. So we have V prime plus, here we have 0.7 divided by 0.67, which is 1.0448 V is equal to negative 9.8. And this is the differential equations that we are going to have to solve. And to solve it, we recognize that it's a first order linear differential equation. So we find mu. Mu is e to the power integral of that, which is just e to the power of that. And now we multiply both sides by the integrating factor, and the left hand side now becomes e to the power 1.0448t times v, and the right hand side is the integral of negative 9.8 times e to the power 0.448t dt. So we can easily find this integral by doing linear substitution. Now to isolate v, we're going to divide both sides by integrating factor. So we have negative 9.8 divided by 1.0448. So we have negative 9.3798 plus c e to the power negative 1.0448 t. Now we can use the initial condition. Initial velocity is 42 meters per second. Let's assume it's going up 42 meters per second. So c will be equal to 42 plus 9.3798. So c is 51.3798, and let's write the function for that expresses velocity. So v of t is equal to negative 9.3798 plus 51.3798 e to the power negative 1.08 t. And now the question is asking us to find how many seconds does it take for the softball to reach its maximum height, and the maximum height will be obtained when the velocity is equal to 0. So we need to solve this equation for t. So we set this equation up. So and t will be equal to negative, so it's going to be 1 over negative 1.0448 times ln and we're just going to put that in the calculator. So we have ln of 9.3798 divided by 51.3798, all that divided by negative 1.0448. So the final answer is 1.6278 approximately. So we have to round to the hundredth, and here's the answer, 1.63 seconds. And yeah, that's kind of it. Here's another problem. In this problem, we really need to focus on the given equation. And I'm going to rewrite this equation like this. And we now need to carefully read the problem and identify all the ingredients here. And let's see. So A is the amount of chlorine added to the tank per minute. In gallons. So we have 8 gallons per minute, but only 45% of it is chlorine, so 0.45 times 8 is 3.6. So 3.6 gallons of chlorine is added per minute, according to this formula, right? According to what's given. D is the amount of solution draining from the tank per minute. It drains 2 gallons per minute. So D is 2. R is the amount of solution added to the tank per minute. We've been adding 8 gallons per minute. And K, finally, is the starting amount of solution in the tank, which is 110. I feel like something is missing here. We never use the fact that there is 10% chlorine. Oh no, we do have this. So Y of 0, so the amount of chlorine in the tank is 10% of 110 gallons. So it's 0.1 times 110 is 11 gallons of chlorine. So now that we know all this information, we plug it all in and solve the equation. It's an initial value problem. So let's go ahead and start solving it. We have y prime equals 2 over 8 minus 2 t plus 110, all that being equal to 3.6. 8 minus 2 is just 6. So we can write this equation like this. And we can also reduce everything by 2. So here we have 3t plus 55. And it's a linear first order differential equation. So to solve it, we're going to find the integrating factor. Integrating factor will be e to the power integral 1 over 3t plus 55 dt. It's going to be e to the power 1/3 ln of absolute value 3t plus 55, which, if we assume that t is positive, which is pretty reasonable, we can bring 1/3 inside of ln and get rid of the absolute value, and then e and ln cancel one another. So integrating factor is just this. And now, after we multiply both sides by the integrating factor and simplify, the left-hand side will be the integrating factor times the function, and the right-hand side will be the integral of the original right-hand side times the integrating factor and we now have to integrate that. So the antiderivative is rather simple. We have 3.6. We have 1/3. We have 3t plus 55 to the power 4/3, and we divide it all by 4/3, so it's 3/4. So you can check that that's the answer. And now we have to isolate y, so we divide both sides by this. So we have, what's 3.6 divided by 4? It's 0.9. 3t plus 55 plus c times 3t plus 55 to the power negative 1/3. And now we can use the fact that at 0 there were 11 gallons, so we can find c. 0.9 times 55 plus c times 55 to the power negative 1/3 means, well, all that is equal to 11. So c will be equal to 11 minus, what's 0.9 times 55? Minus 49.5 times 55 to the power negative 1/3. So this is just so maybe we can compute this. So c is approximately negative 10.1237, and therefore the y function is equal to 0.9 times 3t plus 55 minus 10.1237, 3t plus 55 to the power negative 1/3. And the question was asking to evaluate y of 5. So to find y of 5, we simply go and replace t with 5. But I have a better idea. We can just type this function here. I'll use x instead of t. And let's call this y of x. And let's just check that y of 0 is equal to let's not call it y, let's call it f of 0, f of x. So f of 0 will be equal to, let's see, something is wrong here. Maybe I computed it wrong. The constant, let's see. yeah, that's right. So it's not negative over here. It's positive. So the constant is negative 146.4137. And let's see if that number makes most sense. 146.4137. And look at that, f of 0 is 11, but we're looking for f of 5, which is 27.4738 approximately. And I guess that's the answer. Since we're rounding to the nearest tenth, it's just going to be 27.5. So that's it. We have another problem on air resistance, and let's just have fun with it. We're going to set up the equation like this, and so it's going to be here's the process. The net force is equal to MA, which is MV prime, which is also equal to the sum of all other forces, which are negative mg minus negative 0.9 V, which is the air resistance force. And here's the equation. We have mv prime equals to negative mg negative 0.9 V. We divide everything by m, add 0.9 V to both sides, find the integrating factor, let's just call this some air resistance coefficient. Let's call it A. Again, let's just have fun with that. And now on the left hand side we have e to the power at over m times v. On the right side we have integral of negative g e to the power at over m dt. Now this is a easy integral. We just divide by the, it's going to be this, gm over a plus c. Now we're isolating v. So when you isolate v, you get negative gm over a plus c e to the power negative at over m. And now we can use the fact that initial velocity is given. Let's call it v0. That means c will be equal to v0 plus gm over a. That means v of t will be equal to negative gm over a plus v0 plus gm over a e to the power negative at over m. And now the question was to find the maximum height. So we have to solve this equation for t. So we're going to set this up equal to 0. And we need to find t. So we're going to add gm over a to both sides and divide by that what's in parentheses. So e to the negative at over m is equal to gm over a divided by v0 plus gm over a. This can be simplified like this. And finally, this is the answer. And what I'm going to do is I'm just going to type this formula. Maybe A is not a good name for the air resistance coefficient because A also represents the acceleration, but it's too late to change that. So this is my formula, and according to my problem, m is equal to 0.5, the air resistance coefficient is equal to 0.9, the initial velocity is 49 meters per second, and g is equal to 9.8. So the time that it takes to reach the maximum height is 1.28. If you got this far, feel free to use this formula, as long as you know how to derive it. Let's go to the next question. Question number 4. We also done a problem like this earlier, so let's have fun with this one as well. We have y prime plus d over r minus d t plus k y being equal to a. The integrating factor is equal to e to the power integral of d over r minus d t plus k dt. So this integral will be e to the power, so we're going to have ln, so it's going to be d over r minus d ln of absolute value of r minus d t plus k, but it's fair to assume that that expression is positive, so we can bring the power inside and get rid of the e. So we have r minus d times t plus k to the power d over r minus d. That's my integrating factor. Now step 2 is to multiply both sides by the integrating factor, and we write the left hand side as the integrating factor times the function, and on the right side we have an integral of the original right hand side multiplied by the integrating factor now we can take out a, we can take out the r minus d coefficient, and we have, like, this is just a linear substitution, so we have I'll do it like this, r minus d t plus k, we add 1 over here, so by adding 1 over here this d turns into r, and we divide by r divided by r minus d, so it's going to be same as multiplying by r minus d divided by r, and we have plus c, so r minus d is gone. And now we're going to isolate y by dividing both sides by this. And here's what we get. We get a over r. Now we're going to take this and divide it by this. But notice how the base is the same, but the exponents are different. So it's going to be r minus d times t plus k to the power this minus this. So r over r minus d over r minus d, that's just 1. And we're going to have plus c, and we're going to have r minus d times t plus k to the power negative d over r minus d, but we can just not write the negative in the front and just write the d minus r in the denominator. And that seems like the general solution. However, frequently we're given the initial condition, right? So to find c, we will use the fact that y of 0, which is on one hand a over r times k plus c times k to the power d over d minus r, and it will be given some value, let's call it y0. So now we're going to solve this for c. We're going to subtract, so c will be equal to y0 minus ak over r divided by k, so it's going to be the same as multiplying by k to the power d over, and I'm going to put r minus d over here. So that's my constant. So finally the original function will be equal to a over r minus d t plus k plus, so this is my c, y0 minus ak over r times k and here's I'm going to do some basic algebra. So this is same as 1 over k to the power d over d minus r. We can take out that negative sign and combine it, apply it to k. So this whole thing becomes r minus d over k times t plus 1. to the power d over d minus r. That's the formula. And we are simply asked to find y of 14. But in order for us to do that, we need to identify A, R, D, K, and all that stuff. So what is A? A is the amount of chlorine added to the tank per minute. We are adding solution, 90% solution, so 90% of 8 gallons per minute. That's 7.2. A, R, no, let's go with D. D is next. D is the amount of solution draining from the tank per minute. So we have 5. R is the amount of solution added per minute. So we have 8. K is the starting amount. So we started with 70 gallons, of which only 35% is chlorine. So 35 of 70. What's 35 of 70? $24.5. That's K. And what's the last thing? Y0. What's Y0? Y0 is the initial condition, so Y of 0 is equal to actually no. So what we just found was Y of 0. That's how much chlorine was in the tank. But K is the starting amount of solution, so which is 70 gallons. Now we have all the ingredients, so let's go ahead and let's type up this formula. And again, I'm only doing this just for fun, because otherwise it would be a pretty boring problem. And let's type, we have f of x, a over r, we have r minus d, t plus k plus y0 minus ak over r, and we have r minus d over k times x plus 1 to the power d over d minus r. And let's change this to x. And a is 7.2. Actually, before we do this, I want to go ahead. Remember, we did this problem number 2. So I want to check whether it will work. If we could have done the problem number 2 with this. So let's see. If a is equal to 3.6, r is equal to 8, d is equal to 2, k is equal to 110, and y0 is 11, we're looking for f of 5. Wait, where did it go? F of 5. Oh, it looks like that would have worked. So now that we know this formula works, well, very likely it works. Now we will use it here. So we're going to find y of 14 to be equal to, so let's plug in. A is 7.2, R is 8, D is 5, K is 70, and Y0 is equal to 24.5. So f of 5 is 48.6435, and We have to round to the nearest tenth, so we're going to enter 48.6. I do not doubt the formula, but we might have read all the conditions wrong. Let's see. 35% of 70 is... So 90% of 8, that's how much is added per minute. D is draining. D is 5. And K is the starting amount of the solution. So K is 70. Let me check if I... So this is fine. K is 70, R is 8, D is 5. My god. I found f of 5, not f of 14. So the answer is 83.2. And we finished the homework, so feel free to use these formulas. And if you have any questions, feel free to reach out.